Hi, and welcome to this second video on gradient boosting. So just to summarize where we were, in the previous video, we derived this very natural algorithm, boosting algorithm, that is going to eventually lead to the gradient boosting algorithm. So in this case, we looked at minimizing training regression trees to minimize the least squared loss. So the basic idea in the setup was that first, we find a hypothesis that makes, a constant prediction. So we start by finding a hypothesis that predicts the mean of all the labels of the training data, since the mean minimizes the least squared loss. So we want to first predict this. This is the best constant prediction we can make. We give it a constant of alpha 1, and then we run these t iterations of training, where we train a regression tree to minimize the least squared loss, where the data is the same feature vectors as before, but we change the labels such that the labels are now the true target labels minus the prediction that we would make so far, right, of the hypotheses that we trained already and collected in this ensemble or collection of classifier or regressors that make predictions. So I guess if you haven't yet watched the previous video, you should watch that one first. Right, so that's the basic idea. In each iteration, we train on this kind of residual error, what we need to predict to go from the current prediction to the true labels. And then we have this learning rate eta that we set each of these coefficients alpha t to be. And the final output after some t iterations is this, voting regressor, the one that returns the combination of predictions made by all these individual hypotheses weighted by these constants alpha. So that's the one we saw when we looked at concretely at least squared loss. Okay, so to work our way towards the final gradient boosting algorithm, right? So we'll just introduce a little bit of notation. So we'll use this notation f sub t of x to denote the classifier, the regressor that we've trained after t iterations, right? So it's the one that on a given x predicts the sum from 1 to t of this alpha j times the prediction made by the jth regression tree. Okay, so this is just a notation. And we're going to use this notation also if we have the whole data matrix. Then we say ft of x is just the vector that in every entry, so the data matrix, right, has all the feature vectors as rows. This ft of x is the vector that in each entry just has the prediction made so far, right? So by ft of x, if we apply it to any of these individual feature vectors, each of these entries just contain the predictions that we make on these different end training examples. Okay, so with this notation, ft of x, really the vectors, the new data that we're looking at is the same data matrix, but it has a new vector of labels that we're trying to fit. And this vector of labels is the true vector of labels y minus the current predictions, the vector that contains the current prediction on every training example in each of its entries, right? So this is what the algorithm is doing. Okay, so, right, so if the observation from before was that, or I guess that we see here is that, well, this is going to train a regression tree and it's trying to predict these labels y hat. And let's just pretend for now that actually this regression tree managed to perfectly predict these labels. If it actually managed to perfectly predict it, then because we're adding ht to our combination of regression trees here, then the new regressor that we get afterwards is the previous one plus, and then we have this alpha t, right? So that's the eta times this label vector y hat. Okay, so this kind of update, right, resembles something that we've seen before, right? So in every single iteration, I take what I had in the previous iteration and then I add some eta times something to it. And I guess it also goes in the name gradient boosting, right? So this looks a little bit like gradient descent. So let's try to see what gradient descent could perhaps look like in the setup. So let's say, imagine that I could somehow do gradient descent on the prediction. So I could change the predictions by doing gradient descent. So let's try to see what I mean by this. So with this least squared loss, right, we have the in-sample error. We can think of the in-sample error as a function of the current predictions, like the prediction that we make in iteration t minus 1. And if we do so, right, the formula would look like this, right? You average over all the training examples, you take the true label minus the prediction, and you square it. Okay. Now, if I want to do gradient descent, I need to compute the gradient of this. And with respect to I guess this ft of t minus 1 of x, the current predictions. And so this would be a vector that has an entry, it contains all the partial derivatives, right? So ft minus 1 of x is a vector with n entries, one for each training example. And so if I look at the gradient vector, it would be a vector again containing all the partial derivatives of this in-sample error with respect to each and every one of those entries in ft minus 1 of x. And those entries are just ft minus 1 of x1 up to ft minus 1 of xn. So this would be the gradient vector. You would take the partial derivative of this in-sample error with respect to the prediction that you make on the point x1 and all the way up to the prediction that you make on point xn. Okay, so we treat in each and every one of these, we treat ft minus the prediction made on x1 or the prediction made on xi as a variable. And so if we do this and we look at this expression up here and we need to compute these derivatives, what do we get? So, right, so the main observation is that up here we have a sum, right, over n terms. And if I'm computing the partial derivative with respect to the prediction made on the point xi, then the only term in this sum that contains the point xi is the ith term, right? All the others don't have any. So they just disappear when we take derivatives. And the term that actually contains the prediction on xi, there it's yi minus the prediction squared. And so if we take the derivative here, we're going to get, we have the 1 over n out here in front, and we have a minus, and we get a 2 over n times y1 minus ft minus 1 of x1. Okay, so maybe one way to see it is here that the outer function that and you're applying the chain rule, the outer function is the square. The derivative of this is 2 times the inner function. So you have the 2, you have the 1 over n from out here times the inner function, which is y I minus ft minus 1 of xi. And then you also have to multiply the whole thing by the chain rule by the derivative of the inner function. And the inner function here as a function of ft minus 1 of xi is just minus 1. So that's why we get a minus in front here. So this is just using the chain rule. We get that all these partial derivatives, we just extract a single term from it. Namely, in the ith entry here, we get basically the partial derivative with respect to the ith prediction, the prediction on the ith training example. And this is just has this formula that we see here. Okay, so this would be the gradient if we were doing gradient descent on the predictions, if we could actually change the predictions and do gradient descent. Okay, now if we notice here, by the definition of this y hat up here that we have, right, y hat is the difference between the vector y and the vector of predictions on the data set x. So this means that all of this gradient here is just minus 2 over n times y hat. Okay, so now you can see that this is starting to look like what we have over here if we actually manage to train a regression tree that perfectly fit the labels. Because in gradient descent now, what you would do is you would update your predictions to be the previous predictions minus a small step in the negative direction of the gradient, right? So you have a minus here, and then you have your step size eta, and then you have your gradient up here. So this would be the update that you would be making. As you can see here, the minuses cancel out. You have an eta times 2 over n, and you have your y hat. So this is exactly the same form as what we have over here, except that it's just a different learning rate, right? The scaling here is a little bit different, so it's some other step size. Okay, so basically what I'm saying here is that, okay, if we manage to train a regression tree that perfectly fits the labels, then the update step that we're doing in this gradient boosting, at least this first version of gradient boosting, the step that we're doing basically corresponds to a step of gradient descent where the variables would be the predictions that we make, and if we try to do a gradient descent on those predictions. Okay, so that's the kind of intuition to have in mind for designing the final gradient boosting algorithm. So, right, so basically what we're doing is that if we manage to train the regression tree to perfection, then it's going to actually simulate gradient descent when we do gradient descent on the current predictions in order to minimize the in-sample error. That's the basic idea. And this idea is what we need in order to take this template algorithm and turn it into a general algorithm for gradient boosting. Okay, so let's try to see. So, right, so what we said earlier was that this algorithm gradient boosting, it can work with any pointwise loss function. Okay, so here I'm just going to give you a couple of examples of pointwise loss functions, right? So the pointwise loss functions are the ones where the in-sample error is written as an average over n training examples of a loss function applied to the prediction made on the ith example and the label yi. And here we're just going to assume for use in gradient boosting that this loss function that we're doing on each individual ones is a differentiable function, and that we can compute the derivative with respect to this prediction. So let's just see some examples of popular loss functions and see what these derivatives look like. So we just had least squared loss. So here we already know that the least squared loss function is the difference between the prediction and the true label squared. And so the derivative of this, the partial derivative with respect to the prediction, if we treat the prediction here as a variable, then by the chain rule, again, it's just this -2 times y minus f of x. Okay, so that's the example that we just saw. You could also have other loss functions. So for instance, here, if you're going to do something like negative log likelihood of sigmoid, which would correspond to cross entropy loss for the binary classification case. So here, right, if you have this loss function, you can also compute the partial derivative of this loss function with respect to the prediction. And I won't go into the exact calculation. This is just an exercise to do it. But you get an expression for it, and it looks like this. You get y times the sigmoid function of y times f of x minus 1. Right, so it's just a small exercise to prove this. But you can actually compute an expression for the derivative here, where you treat the loss function, loss as a function of the current prediction. Okay. You could also look at exponential loss, which is kind of what we were doing in add a boost in some sense. So here, right, the loss is e to the minus y times f of x. And if we take the partial derivative with respect to f of x to treat f of x as a variable, then again, by the chain rule, we get e to the minus y f of x times the derivative of the inner function, and the derivative of the inner function with respect to f of x is just minus y. This is kind of like exponential loss. The last one I'll introduce you to here is called Hinge loss, that we haven't really talked about in any of the previous videos, but we will return to it when we get to support vector machines. So the Hinge loss is defined a little different than the previous ones. The Hinge loss, given a prediction in the label, is said to be the maximum of 0 and 1 minus the product of the prediction and the true label. Okay, so I'll come back to this loss function a little later and try to motivate it. But the basic idea is that, well, if you make predictions that are not, like it's a regression problem, for instance, if you make predictions that are not -1 + 1, then this is saying that, oh, even if I have the right sign in my prediction, that y and f of x have the same sign, if the magnitude of the prediction, the value of f of x is very close to 0, then I still pay something in the loss function. I have to make the prediction all the way up to a full 1 in absolute value before the loss goes to 0. And you can also compute partial derivatives of this expression with respect to f of x. Again, here the outer function is the max expression of max of 0 and x, and the inner function is 1 minus y f of x. And so I guess we saw in some previous videos what the derivative of the max function is. It's basically the indicator function that is 1 whenever the max is the second term here, and it's 0 whenever the first term is the max. And so basically this is this indicator function saying whether 1 minus y f of x is greater than 0. And then you have to multiply the derivative of the inner function by the chain rule. And so the derivative of the inner function with respect to f of x is just minus y. So this is called the Hinge loss. So here we can also compute the derivative. We can compute an expression for the derivative. Okay, so for all these cases, this gradient boosting will give us a template for boosting with all these different loss functions. Okay, so back to the template algorithm that we had before when we worked with a least squared loss. Right, so we'll try to see what we can do now. So to work our way towards gradient boosting, we'll try to change it a little bit. Right. So the first step before, if we see here, right, is we return the constant value that gives that minimizes the loss for least squared loss. In this case, it's just the mean of the data points. So here in gradient boosting, what we're going to do instead is we're just still going to return a constant. The constant is just going to be the one that minimizes the in-sample error with this new loss function. Right? So a very natural choice of first prediction. If I return a constant value, I return the one that minimizes the loss. Okay, that's very straightforward. And now what you do now in all these iterations when you're training, you're still training these regression trees, and you're still trying to minimize least squared loss. The data is still x. Now the labels now, and this is the change from before, we're trying to generalize this idea from the least squared loss. The label vector, the vector values that we're trying to predict, what we're going to do is we're basically going to let it be the negative gradient of the in-sample error seen as a function of the current predictions, right? So basically this would be a vector. Again, if you look at what the in-sample error is here, right, it's going to be a vector, and each of the entries are going to contain partial derivatives with respect to each of the terms occurring in the current predictions, right? So in the current predictions on the data matrix X, there's one prediction for each and every one of the training examples. So basically, there's going to be an entry containing a partial derivative with respect to the prediction on X1, all the way down to an entry corresponding or containing the partial derivative of the loss with respect to the nth training example. Okay, so this is what we're going to get. And well, the nice thing about pointwise loss functions, right? So if we look at the in-sample error as a function of the current predictions, if I take partial derivative with respect to the prediction on xi, only one term in this sum depends on it, namely the term corresponding to xi, the point xi, the ith term in the sum. So that's why it simplifies this expression. So basically the first entry in this gradient vector is just going to contain the partial derivative of the pointwise loss function just applied to the prediction made on x1 and the label y1 with respect to the prediction made on x1. And so forth, right? So the nth term down here contains the partial derivative of the loss function applied to the current prediction on xn using the label yn, and it's the partial derivative with respect to the prediction made on xn. Okay. And the minus here we just keep. So again, the observation now is that, okay, if we actually manage to train this regression tree such that all the predictions are perfect, right? Then the changes that we make is exactly going to correspond to gradient descent, because, well, the new prediction, right, is always the old prediction plus the prediction made by the teeth hypothesis. But the prediction made, if it's perfect, is exactly minus the gradient, right? So this is the prediction that we would make. It would be the previous prediction minus eta, which is the learning rate, times this gradient vector containing the gradient of the in-sample error with respect to each and every one of the current predictions. And so this is basically corresponds to doing gradient descent on the predictions if we actually manage to predict these labels y hat perfectly. Okay, so this is the basic idea, is that we're going to train a regression tree to minimize the least squared loss when the labels, each time we want to run an iteration, we define this label vector y hat, which is this vector containing partial derivatives of the loss functions with respect to each and every one of the predictions. Okay, so we'll of course run through an example just to get a better feel for this. Maybe one small observation here, or tiny detail, is that this 1/n factor that we get here when we look at the gradient, actually, if you implement it, it will result in very small changes in the predictions. So usually what you do is you just drop this term, and of course things are it's still gradient descent that we're doing. It's just a different learning rate in some sense. It's kind of corresponds to upscaling the learning rate by a factor n. So you typically would like it to be independent of the number of training examples. So often you drop this. So then the algorithm is just this one, right? So it's a little bit simpler. So in each and every iteration, so even though it's conceptually it's a complicated algorithm, but it's not that many things that are happening, right? You just keep running these iterations, and in every iteration you train a regression tree using least squared loss to minimize the squared difference between the predictions made by this regression tree and this very special vector of labels y hat containing partial derivatives of the loss function at each and every one of the training examples of the current prediction and the label the label of the point with respect to the current prediction. Okay. Of course, you could ask yourself, why are we minimizing the least squared loss when we're building this tree, right? So we just said that, oh, I have some loss function L that I'd like to minimize, but I'm training a tree to minimize least squared loss between predictions and these labels in this vector y. You know, why are you doing this? Why do you use least squared loss? Shouldn't we try to use this loss function L? So in some sense, the downside of doing this is that, okay, in some sense we're minimizing the wrong loss function, right? So which seems like a bad choice. Of course, the positive thing is that, even though we're minimizing the wrong loss function, we still get that, okay, if you manage to make the least squared loss 0, so you perfectly fit this data, then you are still doing gradient descent, right? You're doing exactly what you're supposed to do. And then the second reason, I think this is maybe a very strong motivation for doing this, is that if I use this as my template algorithm, then no matter what loss function I plug into this algorithm, I already have my base learning algorithm for training trees, right? I don't have to adapt this one to new loss function. I can just always use least squared loss. So I don't have to come up with a new base learning algorithm, new tree construction algorithm for every possible loss function. So that's the reason why we are actually going to stick to minimizing least squared loss, even though the loss function is something else, the one that we finally care about. Okay. So we're almost at the final gradient boosting algorithm. We just need to do one last tweak to it. Right. So as I just said, right, it's really nice that we can use the same tree building algorithm, this least squared loss algorithm, to construct the tree. Now, what you will do at the end here is that we're going to make a small tweak to it. And the tweak that we're going to make is that once you've finished building this tree, and least squared loss, we say, okay, return the mean value in each of the leaves. What you're going to do now is you're going to change the predictions that you make in the leaves. So here it is. Here is actually the full gradient boosting algorithm. So the only addition that we make now is that once we're done building, when we trained the tree HT, what we do is we loop through it and we look at all the leaves, and then we change the value predicted there. And what we do is that we say, okay, I'm anyways going to return some constant value here. And this constant value CL is going to change the prediction made on all the points that end up in this leaf. All right. So what we're going to do is we're just going to pretend that we're just going to treat this as a function here. This is the new prediction that we would make, right? We would take the previous prediction plus the CL. And one important thing is here, the learning rate is not included here. Actually, the prediction that we will be making will have a learning rate multiplied onto this constant, but we're not going to do that. This is just to avoid overstepping the target, as we also talked about in the previous gradient boosting video. So the basic idea is just loop through the leaves, and in every leaf, you gather the points that end up in this leaf, and then you look at, well, if I return a constant value CL in this leaf, what is that going to do to the loss function on those points that end up here? And now I'm going to choose the constant value that minimizes the loss, which is a very natural tweak to do. Okay, so this is the full gradient boosting algorithm, right? So in each and every round, the tricky part is defining this vector of labels y hat that contains all these partial derivatives of the loss functions with respect to the current predictions. Okay, so I think we need to see an example execution of this. So let's run gradient boosting, and let's say that our learning algorithm, the base learning algorithm, it is a regression tree, and we're just going to do really simple trees. We're going to do regression stumps, right? So just a single question, either a vertical line or horizontal line, and then you have to make a prediction in each of the two sides, and this is a real value prediction. Right? So in this example, we're going to look at a classification problem. So you can even use this gradient boosting algorithm for classification problems where it's 1 and -1 that you have to predict. That doesn't matter at all, right? You can easily use gradient boosting here, even though the little trees that make up the gradient booster are actually regression trees that can return arbitrary values. So that's what we're going to do. We're going to use these regression stumps, and let's just play with this Hinge loss instead, right? So let's look at the example where the loss function is the Hinge loss, and let's see what happens if we try to run gradient boosting with the Hinge loss function, right? So the Hinge loss again was defined as the maximum of 0 and 1 minus the label times the prediction. So the observation here is that this is going to be 0 if the product of y and f of x is at least 1, which means, well, if the product of y and f of x is at least 1, it means that f of x must have the correct sign, the same sign as the label. And also, the interesting thing is that this forces that the prediction is not close to 0. It forces it to be pretty far away from 0. It has to be at least 1 before you don't pay anything. And then the final classifier that we're going to do at the end, once we've collected all these regression trees, is that we're going to return the sign of the prediction that it makes. Okay, so this is the gradient boosting using regression stumps with Hinge loss. So let's try to see if we can actually run this algorithm. So here's the data set, and the blue dots are thought of as having label +1, and the red triangles have label -1. So what does the algorithm say, right? So the algorithm says that the first thing we should do is to find a constant value that minimizes the in-sample error if I predict that constant value on all the examples. And then we should set the coefficient that we are using on that constant value to be 1. So let's try to see. So this is the in-sample error, right? So the in-sample error is just the average over all the training examples of the maximum of 0 and 1 minus the label times this constant that we're going to return. And now we want to find out what's the best constant. So one way to do it, at least if we're doing it by hand, is to, well, look at what is the derivative of this function and use that to try and figure out how can I minimize it. Okay, so right, the derivative of this max expression here, if I look at the max function and I take the derivative with respect to the current prediction f of x, so then we already saw before that just by using the chain rule, like this max function, the derivative of this is this indicator function. So max of 0 and x has derivative, the indicator for whether x is greater than 0. Now we have to replace x by the inner function, so we get the indicator for whether 1 minus y f of x is greater than 0. Then we have to multiply with the partial derivative of the inner function, 1 minus y f of x with respect to f of x, and this is just minus y. So this is the derivative in general. And for us right now, we're looking at this whole loss function. It's the average over n training examples. And the prediction that we're going to make is the variable c, a constant c. So let's look at the derivative of all of this with respect to c. So just by using this formula that we had from before, this becomes the average over n training examples minus yi times the indicator for whether 1 minus yi times c is greater than 0. So let's try to look at that in this example here. So what do we get? So, right, so there are 5 points here that have a label of +1, and there are 5 points that have a label of -1, which means that half of all the terms have a label yi that is 1, and half of the terms have a label that is -1. So for the terms that have a label of -1, right, so then we have minus times -1, that's a plus, and then we have 1, the indicator for whether 1 plus c is greater than 0. So that's the term we have here. So the first term here times the half is the contribution to the derivative from all the red points. Right, so this is the contribution from all the red points if we give it if we predict any given value c. The contribution from all the blue points is the second term here. Half of the points have a label of 1, so we get minus the indicator for whether 1 minus c is greater than 0. Okay, so now this is the derivative. And what we can see here is that, okay, so what value does this derivative take? I want to find a minimum of this function. So I kind of want to understand what does the derivative look like. So what you can see is that if I plug in a value of c that lies between -1 and 1, then the first term here is going to take the value 1. Right? For c between -1 and 1, strictly between them, this is going to take the value 1, this indicator. And similarly over here, right, if it lies between -1 and 1, this one is also going to take the value 1. So we get 1 minus 1, which is 0. Okay. On the other hand, if c is less than -1, what do I get then? Then you can see that if c is less than -1, then this expression here, 1 plus c, is not greater than 0. So we get a 0 contribution over here, whereas this indicator here actually becomes 1, because 1 minus c, when c is less than -1, is definitely positive. So this is going to give us a -1 contribution. So the derivative is going to be negative when c is less than -1. Finally, when c is greater than 1, we see the first of these indicators is 1. The second indicator is 0. So the gradient is, the derivative is positive in this case. So which means now, what does this function look like as a function of c, this in-sample error? Well, as you can see here, if you start out on the far left in the negative numbers, then the derivative is negative, which means it's a decreasing function until you get to -1. When you're at -1, between -1 and 1, the function is flat, the derivative is 0. And then when you get to 1, again, the function becomes increasing, which means that this function here, this in-sample error, takes its minimum at any place between -1 and 1. So we can return any value between -1 and 1. That's all great. So we can just choose the constant c equals 0. So let's do that. So this is the constant that we're going to return on this training data. Okay, So that was the first step. We just figured out we should return the constant 0. That's the prediction that we do up here first. That minimizes the in-sample error if you have to do a constant prediction. Okay. So now the tricky part is, or now we just have to start training regression trees, and we have to figure out what is this vector of labels that we need to fit, right? So we have to find this or figure out what is this vector of labels that is minus, and then take all the individual loss terms and all the individual training examples. You take the derivative, the partial derivative of this loss function with respect to the current prediction. So let's try to have a look at what this means on this concrete iteration of the algorithm that we're doing. So first of all, right, we'd already decided that our loss function is the Hinge loss function, right? So when we have Hinge loss function, we can already plug in what this is, right? Because we know that for the Hinge loss function, well, the loss function, right, is the maximum of 0 and 1 minus yi times the current prediction on xi. And we already said that the Hinge loss is then you get a minus from the yi, you get a minus, and then you have that cancels out with the minus in front. And then you just have this, the yi, the label, times this indicator for whether 1 minus yi times the current prediction on xi is greater than 0. Right? This is what we get if we plug in the Hinge loss function in all of these. Okay, so this is the vector of labels that we need to compute. Right? So we need to figure out what is this vector of labels. So let's compute that in our running example. Okay, so this is the vector of labels that we need to complete. It should have an entry for each and every one of our training examples. And the current predictions on all our training examples, right? This is one of the terms that appear here. The current prediction on all of them, you can see here, we just predict the constant value 0. So this ft minus 1 of xi is always 0. So that kills the y1, or the yi in general. And so we're just left with the indicator for whether 1 is greater than 0. Right? And then we have multiplied with the true label. So this was easy in this case, right? Because 1 is always greater than 0. So what we actually get here is the first vector of labels is just the true vector of labels. Okay. Good. So these are the labels now that we're trying to fit using a regression tree. Right? So we've computed now the labels that we need to fit. So if you remember, right, the best way to train a regression stump is to try all the possible leaves. And for every possible split, you have 2 leaves where the points end up in. And in both of the leaves, you should return the mean value. That is what minimizes the loss on those subsets of points. So the best possible split that you can actually do on this data that I have here is the one that you see here. Okay, so in this example here, you have the mean is 1 over here, and the contribution to the loss is 0. Over here, the mean is going to be minus 3 out of 7. If you sum up all these values here. Okay, so that's the prediction that you would make in this leaf. Okay, so now we trained, so basically this is what we did, right? We trained one regression stump to minimize least squared loss, and this is what we end up with. We end up with the regression stump returning 1 over here, returning minus 3 out of 7 over here. Okay. And now the trick was now that, okay, we're going to take that stump that we just trained, right? The one that returns these mean values, and then we're going to change the predictions in the leaves so as to minimize the contribution to the loss function by the points in that leaf. So, right, so we already know what this loss function is. It's the Hinge loss in our example. So it's the maximum of 0 and 1 minus the label yi times the current prediction plus whatever we choose to predict in this leaf. Right, so we have to figure out a way to minimize this expression. So we want to minimize this expression here. And so this simplifies again a little bit, because the current predictions, we just ran the first round, the current predictions are 0. So this current prediction term is just 0. And so we just get minus yi times this prediction that we're going to make, CL. So we want to minimize this expression. Okay, and we want to do that separately for each of the leaves. So in the first leaf here, right, so all the labels in the first leaf, they're all 1. So we can see here that there's a 1 on each of these yi's. So we have 1 minus 1 times CL. So we have to minimize the maximum of 0 and 1 minus 1 times CL. And as you can see here, as long as we choose CL to be at least 1, each of these terms becomes 0. So we can choose any value that's at least 1. Let's just return 1. Right, so we return 1 in this leaf over here. Okay. And now the interesting thing is when we look at the second leaf here, right? Because if we had just stopped and not replaced the return value in the leaf, we would have returned -3 out of 7 in this leaf. But this is not what we're going to do here. Here we're going to look at all those examples that are in here in the leaves, and we have to minimize the sum of their contributions to this maximum of 0 and 1 minus the label times the prediction. So at least one way to try and minimize it is, again, to compute the derivative and to try and understand how does this behave as a function of c. Right, so again, the derivative of this max of 0, 1 minus yi times cl with respect to cl is just this expression, you sum over all the elements in the leaf, it's minus yi. This is what you get from the derivative of the inner function, and then you get the indicator function for whether 1 minus yi c is greater than 0. Okay, so if we look at this leaf over here, right, there are 5 points that are red here. Those have a label of -1. Right, so we have 5 points where we, in place of the label, we put in -1. So -1 is plus, and the indicator here, this expression down here for the indicator becomes 1 plus c. So we have 5 terms that contribute the indicator for 1 plus c greater than 0. Then we have these 2 terms that have a label of +1. Their contribution is here we have the minus, the label +1, so that's a minus. And down here we get 1 minus c. So this is the derivative of this as a function of c. Okay, so let's try to understand how this behaves. So what we can see is, okay, let's try to look at c greater than -1. So if c is greater than -1, right, then this first term over here, this first indicator becomes 1. And then this is a 5. And then no matter what the second one is, this is a positive expression. Okay. You can also see if c is less than -1, then the first term becomes 0. And well, the second term over here, if c is less than -1, this becomes a 1, this indicator, so we get a -2. So it's negative over here. So what this means is that this function here is a function of c. It is decreasing for c less than -1, and it's increasing for c greater than -1, which means to minimize it, we have to choose c to be exactly -1. So this is the value we return, right? So you can see here, this is not the mean value that we're returning. We're actually going to return -1 instead. Okay, so this is what we get. We return 1 in the left part of the tree and return -1 in the right part of the tree. Okay, good. So that was one round of gradient boosting. Of course, we train again, right? So now we have to compute a new vector of labels where we, in each entry again with the Hinge clause, we have to take the current label multiplied with this indicator for whether 1 minus the label that we have times the current prediction is greater than 0. So let's try to look at it. So these are the 2 trees that we've trained so far. And for us, let's just try to pretend that the learning rate was 1, just to keep things simple. So let's go with the learning rate of 1, right? Otherwise, these predictions would be a little different. These predictions would only be weighted by eta. So, right, so the vector of labels that we have to construct should look like this, right? It should have, in every entry, it could contain the true label of the point times the indicator for whether 1 minus the true label times the current prediction is greater than 0. So if we can try to look at these 3 points over here on the left, the 3 blue points here, right? So their current label is 1, and the current prediction is also 1, which means if we look at the indicator, like if we say 1 minus, and then we have a 1 for the label and a 1 for the prediction. So 1 minus 1 is 0, and 0 is not strictly greater than 0. So this is the indicator, it just returns 0 here, and we get a 0 label. Similarly, we can try to look at the red points over here. The current prediction is -1, and the true label is -1, which means that this indicator becomes 1 minus -1 times -1, that is +1. So 1 minus 1 is again 0, and 0 is not greater than 0. So we have, again, a label of 0 on these points. Finally, we have those 2 points here at the top. And if we look at those 2 points, they have a label of 1, but the current prediction is -1, as you can see here by the second regression tree. So we have these 2 points with a label of 1. And so the label we now assign is, well, the label out here is 1 times the indicator for whether 1 minus, well, the true label is 1 times the current prediction, that is a -1. So 1 times -1 is -1, and you negate it, so you get a +1. So checking whether 2 is greater than 0. So indeed here, the indicator takes the value 1, and the label is 1. So these labels, the final labels here become 1. So these are the labels that we now need to work with. So of course, right, then we train a regression tree again to fit these values. Right, so here we train the best regression tree on these labels is clearly this one. This gets it perfect, right? We get a mean of 0 down here at the bottom, and we get a mean of 1 up here. Okay. So what we do now is, remember, we don't use these predictions. We actually go through all of the leaves of this tree and change the predictions to minimize the loss function. Right, so the loss function, so what we have to figure out for every leaf, we have to find the value to return such that we minimize this hinge loss. So sum over all the points in the leaf, the maximum of 0, and 1 minus the label times the current prediction plus what we would get if we add this new constant to it. So let's go over the two leaves. So we can start by looking at the top leaf over here. And okay, so we have to figure out what is the best value to return in order to minimize the loss function, the contribution to the loss function by these 2 points. Right, and again, the easiest thing to do is to look at the derivative of this thing and try to understand how it behaves. So if we look at the derivative up here, right, again, we get it's the sum over the points in this leaf minus the label times the indicator for whether 1 minus the label times, well, here we want to know the current prediction plus this new addition that we add to it, whether this is greater than 0. Okay, so for all these leaves up here, right, both of them have a label of 1. And these are the true labels, right? So the true labels are 1. We insert these true, so both of these contributions, this is going to be a 1. And in here, right, for the indicator, we're also going to put a 1, and the current prediction is -1, right? So that's what we see here. The current prediction is -1, and then we have the C. Right, so 2 terms that contribute the minus and the indicator for whether, I guess, this 1 minus -1 plus C is greater than 0. If we try to understand what is this expression, what values does it give us? Well, the 2 minuses here become a 2, so, and then the minus moves into the C, so it's the indicator for whether 2 minus C is greater than 0. So if you can see, if C is less than 2, then this is negative. This expression evaluates to 1, and so the whole expression is negative, right? The indicator becomes 1. On the other hand, if C is greater than or equal to 2, then 2 minus C is going to be less than or equal to 0, so the indicator evaluates to 0, and the contribution is 0. So which means that the loss function, the contribution to the loss function up here, it's a decreasing function as long as C is less than 2, and then it flattens out. So what we can do here is we can return any value that's at least 2. So let's just return 2 in the top. So we return 2 in the top, and then we can try to look at, okay, what about the second half here? So here we have all the points down here. Right, so we can again try to look at as the derivative as a function of C. And so what do we get, right? So we get this expression here for every one of the points, right? We have minus the label times the indicator for whether 1 minus the label times the new prediction if we add C is greater than 0. The current predictions down here varies between the points. So there are 3 points here, the 3 blue points. Their current prediction is 1, and the label is also 1. So if we insert the label, we have a 1 out here for the yi, we have a 1 for this yi, and the current prediction in here, right, we have the minus, the current prediction is 1, as you can see up here. These lie in the left half where we already have a prediction of 1, so we get a 1 plus our C. So this is the contribution from the 3 blue points. If we look at all the red points here, the 5 red points, then these 5 red points, right, so what do they have? They have a label of -1. So they have -1, that's a plus. There are 5 of them. And then we have to look at the indicator here. So the label again is -1, so we get a 1 plus. The current prediction is -1, as we can see up here, plus the C. So this is the indicator. Right, so what do we have here? If we simplify this, the last indicator here is just C greater than 0, and the first indicator is minus C greater than 0. So let's try to see. So if C is less than 0, then minus C is greater than 0. And then this indicator is 1, and we get a -3 contribution from this term. And for C less than 0, C is not greater than 0, so we get a 0 contribution here. So we get a negative derivative. So for C less than 0, this is negative. And for C greater than 0, the first indicator becomes 0, the second indicator becomes 1, and it's a positive expression. So this means that this, as a function of C, is first decreasing until c is equal to 0, and then it's increasing thereafter. So which means it takes its minimum at c equals 0, so we're just going to return 0 here. So this is the true leaf that the true decision, the regression stump is going to return 2 here at the top and 0 at the bottom. So this is the final 3. Let's just stop after 3 iterations. Then we have, this is the constant function returned first. This was the first regression stump we trained, and this was the second one that we trained. If you overlay these and you look at the prediction that they make, you're going to sum their predictions. Then we can see if we're up here in the top left corner, this is going to predict 1, and this is going to predict 2, so you're going to predict 3. Up here in this part of the region, you're predicting 2 from this one and a -1 here, so the prediction is 1. Down here in this corner, the prediction is a 1 here and a 0 and a 0, so we get a 1. And in this lower corner, it's -1. So if we take the sign of this, which is the final classifier we're using, you can see it's going to predict blue out here, and it's going to predict red in here, and it's going to get all the points right. So this is like what's an execution of gradient boosting using regression stumps and Hinge laws. So this is the full algorithm, the gradient boosting algorithm. First, find the constant that minimizes the in-sample error. If I return this constant, set the contribution to 1 to the final regressor. And now for each of the iterations, we train a tree using least squared loss, where the labels are this vector of all the partial derivatives of the loss function on the individual points with respect to the current prediction. And then once we've trained this regression tree using least squared loss, we go over all the leaves of the tree, and we change the prediction such that we return the constant that minimizes the new loss function, the contribution to the loss function, by those points that end up in this leaf. So the nice thing here is that all we're doing really is that we just need to compute the derivative of the loss function with respect to c, if c is the first return value here. This is really mostly what we have to do, and if we can just do that. Then if we actually have the derivative, then an interesting point here is that, so right now we have to hard code and what we did with these Hinge laws was that we computed the derivative, then we saw it was decreasing and was increasing again. What you would actually do in practice, if you wanted, you wouldn't sit down. Of course, you wouldn't have an algorithm that computes this exactly and figures out when it's increasing and decreasing. But what you can do is, since we can compute these derivatives of the loss function, and it's a function of just one variable, then what you actually do is you just run gradient descent on that one variable to figure out what to return. Right, so you just use gradient descent inside gradient boosting to figure out what these constant values should be. It's gradient descent on a single variable, right? So it's a very fast type of gradient descent. So all we really need is to be able to compute these derivatives, and then we just do gradient descent on the constant values. Of course, if it's not a convex function, maybe you run into some issues with local minima, but if this is good enough, it's fine. And otherwise, you just run this gradient descent for convex loss functions. Definitely is going to converge towards the minimum. So just going to use that as long as you can compute these derivatives of the loss functions with respect to the prediction that's being made. Right, and then you just run gradient descent. So this is really nice, right? So this means that, and I guess also as part of the algorithm, right, you already assume if you want to construct this vector of labels y hat, you actually need to be able to compute the derivatives of the loss function with respect to the current prediction. So you're already assuming you can do this, right? And so this whole gradient boosting algorithm, the template here, it just works as long as you have a loss function where you can compute partial derivatives with respect to the current predictions. Right? So super clean, very useful algorithm, although it's a little tricky to get your head around that defining this vector of labels y hat that you want to predict, that is the negative of this gradient vector, and then you're training with least squared loss, you're training a regression tree to minimize this. And then finally, you're changing the return values in the leaves. Right, so that is the full gradient boosting algorithm. So it's a general template for boosting where you have any pointwise loss function. And you just need to be able to compute the derivative with respect to the prediction y prime. And so I guess what this means is that since it's just a template that works for any pointwise loss function, you can really focus your efforts. If you want to implement it and optimize it, you can just focus on being really good at training regression trees with least squared loss, right? That's a basic. You can just focus on this one task. And of course, you could ask yourself, why do I use trees, right? Why is it regression trees that I use as base learners in gradient boosting? And the point of this is that the leaves inside a regression tree, they return constant values, right? It's always you end up in a leaf and then you return a constant value. So which means that if I want to, following this template, if I want to optimize for some concrete loss function, the only thing I need to be able to do is to optimize the constant in the leaf, which is a much simpler task than if you, I don't know, had some other learning model. Here, you just need to be able to pick a constant to minimize a loss function over a bunch of points that end up in the same leaf. So just finding the best constant to return is a much easier task, and you can typically do this gradient descent in just a single variable to minimize this such a loss, right? And also, one nice thing about gradient boosters, we didn't talk too much about it with previous, for instance, these linear models that we've seen, is that in all the linear models, right, you do inner products between feature vectors and some vector parameters. And these inner products really depend on the scaling of the input features. So typically you have to be a little careful when you start out. You have to actually scale your data features so that you don't run into issues. Trees, on the other hand, they don't care about the scaling of values, right? They just compute splits. So the scaling of the features is completely irrelevant. So you can just take them off the shelf in some sense and just use them, right, without pre-processing the data, really. And this also means that gradient boosting is, in some sense, one of the best off-the-shelf classifiers. If you don't want to worry about doing anything to your data, this is really one of the first go-to things. You could just take it and run it, and it will work well. And there are really efficient, freely available implementations of gradient boosting, particularly these libraries XGBoost and LightGBM. Right? So let us end the discussion of gradient boosting there.